Hello and welcome to our first video reviewing important concepts from our matter unit. And so we're going to take some time and just review some of those important concepts and go over them. And remember, you have all your old notes to look over as well. And before you try the remediation assignment associated with this lecture. And so remember, when we're talking about matter, we're talking about everything that's in the universe. Elements, compounds, mixtures, all matter, right? And it falls into that, whereas what we're kind of talking about. And that we can kind of separate each of those things into two big groups. We can separate them into either pure substances, which we're talking elements or compounds. And so if we're talking about an element, well, we can see that we have only one type of element, whether it's all helium or all copper or all oxygen gas or all sulfur. And remember, elements can be atomic, like helium and copper, where there are single atoms that are together, that are bunched together, or they can be molecular, like oxygen gas, where the simplest form of that element is two oxygen atoms bonded together. And so oxygen and sulfur happen to be molecular elements. So they're still elements. There's only one atom there. It's just that the simplest part that makes up those elements are, in this case for oxygen, two oxygen atoms bonded together. In the case for sulfur, it's 8 sulfur atoms bonded together. But they're all still only one atom in there, which is why they're still elements. It's just that those atoms, for some elements, those atoms group together and bond together to make simple little molecules. Okay. For compounds, we take two or more different elements and we get a molecule, and molecules are the simplest form of a compound. And so, for instance, we have water, which has 2 hydrogen atoms and 1 oxygen atoms chemically bonded together. Nitrogen dioxide, we have 1 nitrogen atom and 2 oxygen atoms chemically bonded together. And so for the compound, the simplest unit that still has properties of that compound are these molecules. And then this is a sucrose molecule, which again, much bigger, but all of those atoms are bonded together. And that molecule is the simplest unit that still has properties of that compound, which in this case is sucrose. If we take 2 or more pure substances and mix them together and they're not chemically bonded, we get mixtures, which can be either heterogeneous and homogeneous. So we'll take some time to kind of first look at these different and differentiate heterogeneous and homogeneous mixtures. These examples where we see that we have on the right here, we have an example of a heterogeneous mixture. How do we know it's a heterogeneous mixture? Well, we see 2 distinct phases. So remember, a phase is just part of a mixture with like uniform properties. And so we see this liquid phase and we see this solid phase. And they're very distinct and they have a boundary, and we can very much distinguish that they're 2 different things mixed together, and it's a heterogeneous mixture. We talked about the 2-scoop rule, the idea that if you take 2 samples and they don't look exactly the same with the same distribution of components, solute and solvents, that they're a heterogeneous mixture. If we look on the left here, we see this beaker that there's this liquid. It doesn't look like anything else is in there because we only can distinguish one phase. And so it might be a pure substance or it might be a mixture. If we kind of look and see what happens, notice that as this liquid is poured out, notice what happens down here. See how it's getting cloudy? That the cloudiness is because we are seeing very small white crystals forming of the ionic compound that was apparently dissolved in what we now know is a solution. So this is not a chemical reaction. This is a physical reaction. Right? This is this substance, this ionic compound that was dissolved in that solution, is now forming crystals, forming a precipitate. Right? And we can see that crystallization process is continuing, and if we look at the bottom of the beaker, you'll see that very small, fine kind of crystallization is going on the bottom of the beaker, where you can kind of see these boundaries. These are called grain boundaries, in case you're wondering. but that ionic compound that was dissolved in that solution continues to crystallize, right? And that's a physical change because the ionic compound was dissolved in the water and now it is not. It has formed crystals. Right? And so, we now know that this solution, right, was a homogeneous mixture that had that ionic compound dissolved in it. Okay? And so there are other ways besides crystallization of separating solutes from solvents because not all mixtures have a solid part and a liquid part. Okay? Some mixtures are all liquids, right? And some mixtures are all solids. And so, distillation is one way of separating a mixture based on, again, its physical properties. In this case, it's making use of a boiling point. And so distillation is particularly useful if you have, a solution that has all liquid components to it. And they have different boiling points. You can take your solution that start to boil, and as the boiling point of different components are reached, they go into the gas phase and they condense, and you collect the different parts. So sometimes you'll see distilled, like water is described as being distilled because they take the impure water and all of the stuff that's mixed in with it, and they boil it, and they boil off each of the components to get the pure water that's behind. Decanting, we've talked about, it's based on density. And so when we were looking at our heterogeneous mixture, we could decant or pour off the liquid part and leave just those blue crystals behind. So other types of separations, we did a chromatography lab, it was with the inks where you spotted the ink samples on the paper, and then the ink separated by color, or different colored inks. And so that's separated based on solubility, which is also a physical property, and filtration, where you have your mixture and you pour it through a funnel that has a piece of filter paper. The filter paper traps the solid particles and lets the liquid part go through. And so that's a way of separating based on the size of the particle. Again, another physical property. So we can separate mixtures from pure substances by using a physical change. Right? So boiling point change, we can use, and which makes use of physical properties. If we're talking elements and compounds, in order to go between elements and compounds, we have to undergo a chemical change. So we have to actually make and break some bonds. And so when we do that, we've talked about different types of chemical reactions, and remember the big thing, when something is undergoing a chemical change, you're performing a chemical reaction. And so, one of the indications that you have a new substance is that you notice the change in the physical properties from the reactants, your ingredients, to the products. Right? So if we're just doing the simple reaction of hydrogen gas and oxygen gas reacting to make water, we see that hydrogen gas and oxygen gas have their own kind of unique physical properties, and water, right, has a different set of physical properties, and we notice those new physical properties, and that kind of what indicates to us that there's something new forming. Okay, that's one of the indications that something new is forming. And like all chemical reactions, they are going to obey the law of conservation of mass. So if we had 10 grams of hydrogen gas and 10 grams of oxygen gas, and we mixed them together and they all reacted completely, we'd expect 20 grams of water vapor or liquid water to form. Okay. if everything reacted, if all the reactants reacted to produce water. Okay. We wouldn't expect any mass to be lost, right? Unless you didn't account for some gas or some, but we wouldn't expect any mass to be lost. Okay. And remember that law of conservation of mass applies to all normal chemical reactions with the exception of nuclear reactions. Okay.